I think we're ready to begin with our next speaker. I'm Jim Crowley, the Executive Director of SIAM, and it gives me great pleasure to introduce our next speaker, the SIAM invited lecture. For people that are familiar with Sandia National Lab, you will know that Sandia has many outstanding mathematicians and computer scientists, and our next speaker, Tammy Kolda, is among them, among the best there. She's a distinguished member of the technical staff at Sandia National Laboratories in Livermore. She has many awards for her research, including 3 Best Paper Awards, and she received the prestigious Presidential Early Career Awards for Science and Engineering. And I should note that she's very active in SIAM activities. She served as a journal editor on 2 SIAM journals. She's been a co-chair for several SIAM conferences, including the SIAM Conference on Computational Science and Engineering and the SIAM Annual Meeting. She's served as chair of activity groups, and she's also been elected as a SIAM Fellow. And now she serves on the SIAM Board of Trustees. Despite all of these service activities and the role that she's played in all these things, she's been a very active researcher, and her work spans several areas, including data mining, optimization, nonlinear solvers, parallel computing, and software, plus multi-level algebra and tensor decomposition, which is the subject of today's talk. And so I introduce Tammy Kolda.
Thanks, Jim, for a lovely introduction. Thanks, everybody, for coming today. I'm going to talk to you about tensor decompositions, a mathematical tool for data analysis. I want to acknowledge first my collaborators whose work will be featured today. We have Alex Williams from Stanford University, who was a summer intern, Gray Ballard, who was a summer intern, then a postdoc, is now a professor at Wake Forest, Casey Battaglino, who's a student intern from Georgia Tech, Jed Dersh, who's a postdoc at Sandia, David Hong, another student intern from University of Michigan, and Cliff Anderson Bergman, one of my colleagues. Without their work, you wouldn't be seeing what you're seeing today, and of course, I also want to acknowledge all the other collaborators I worked with whose work is not featured today, but some are here. So what are we going to talk about? So we're going to talk about tensors. What is a tensor? A tensor is just a d-way array for some value of d. So we know some tensors already. A vector is a tensor of order d equals 1. A matrix is a tensor of order d equals 2, so those are easy. When we get to d being 3 or higher, it gets more interesting. I can't even make a super good picture. So we have all these dots, and now they're arranged into a 3D structure. So that's a tensor of order 3. Then you have to use your mathematical imagination for a tensor of order 3 or higher. So it gets a lot harder for me to draw, but you understand what I'm talking about. So that is a tensor. So we're going to talk about using tensors in understanding data analysis as a mathematical tool is tensor decomposition. So what do I mean here? We're going to try to take this tensor object, this d-way array, and break it up into meaningful parts. So I'll tell you soon what those meaningful parts are. The mathematics will play roles in defining how to measure how well we've done in approximating our original data, and in terms of creating good algorithms for doing these decompositions. And then we'll give lots of examples. The official advice for giving a talk here said to give examples. You will get lots of them. And we'll show how you can use this to understand your data better, to visualize it, and so on. There are lots of related concepts in matrix land. So if you've heard of principal component analysis as statisticians, this is a higher order version of that. There's singular value decomposition for the linear algebra community. There's independent component analysis, non-negative matrix factorization, sparse factorization, matrix completion. All of these ideas and many more have been extended into TensorLand. So we have this idea of a matrix tensor decomposition. We talked about putting things into parts. So what are these parts? They are rank 1 tensors, and so that's just the outer product of vectors. So in matrices, you know these. You take 2 vectors, say an A of size m, a B of size n, and then you can do their outer product, which we'll denote with a circle, and you get an m by n matrix. So we have m by n numbers, but they're described by only m plus n pieces of data. And so the ij entry of this rank 1 matrix is just given by ai times bj. In the tensors, the idea is the same. So in the three-way case, now we have an m vector, an n vector, and a p vector. Their outer product is again denoted with circles, and we get an m by n by p object. So now we have something m times n times p that's described by only m plus n plus p values. So we write this as this funny-looking chicken foot is what I always call it. This funny-looking chicken foot is a rank 1 tensor for d equals 3. For the d-way case, it gets ugly. So now we have vectors a sub 1 through a sub d, and then we should take their inner product, and this gets quite messy in terms of notation. And so for your all's benefit today, I'm just going to stick to the three-way case, a, b, c, so we don't run out of letters, so that you don't have to squint to see too many subscripts. But it all extends to the d-way case. So let's go back and think about matrix decomposition. Some of you may have seen this type of thing before. We have some data, and we want to find a low-rank model. So it means it's the sum of a few of these outer products that gives a good descriptor of the data. So each entry of our matrix X, which is our observed data, is approximated by some m, which is the sum of entries from these rank 1 matrices. So we can write that in this complicated index notation, or we can write it in matrix notation. So X is approximated by m, which is the sum of outer products of vectors. Typically in matrix world, it's written as A, B transpose, but I'm going to give different notation because A, B transpose does not generalize nicely to higher dimensions. So we'll just write it A comma B in this double bracket notation. So that's what we do in matrices. We have sum of squared errors is our error metric. We'll talk about other possibilities later, but we'll just look at the difference for every single entry, square those, and sum them, and that's what we're trying to sort of minimize to measure how well our model approximates our data. So Jill talked about Google searches. I will talk about Google searches too. I searched for low-rank structure. This turns up over 5 million web pages and over 100,000 Google Scholar references. So matrix, finding low-rank structure in the world is eerily useful and quite surprising in its utility. If we go to tensors in the three-way case, it's not much different, only now we've added this third vector C for each of our rank 1 tensors. So that's the only difference there. We can write this, we'll call each of these rank 1 pieces, by the way, a component. So we often look at the individual components. Those are our building blocks. And then we can write this in tensor notation. It's the same basic idea. And the thing that we're looking for is these factor matrices A, B, and C that describe our data. We're still using sum of squared errors. The only difference now is we're just summing over this three-way object. And tensors, while new, have the potential to be an even more powerful tool for data analysis because now it's higher order structure that you're looking for. And in fact, if you search on Google Scholar, there's already over, or just on Google, there's already over 500,000 results for low-rank tensor structure. And then if you look on Google Scholar, there's over 14,000 papers. So this is an area that's picking up some steam. I thought it might be interesting here, I'm saying there's the CP tensor factorization. What is CP? So a little bit of that depends on who you ask. I'll give you just a little romp through history of this thing. What's really interesting to me is this was invented in 1927 by a fellow named Frank Hitchcock. He was an MIT professor. He wrote this very nice paper that is still quite readable today. Sometimes older papers don't translate well to the modern age, but this one I think translates quite well. And on the first page, he has this equation that turns out to be very clearly recognizable to those in the field as this CP tensor decomposition. He was, among other things, also the advisor for Claude Shannon of information theory fame. And this paper gets a lot of citations on Google Scholar. I can't remember the exact number, but it's only Hitchcock's second most cited paper, although perhaps that will change as these methods get more and more popular. So Hitchcock did this work in 1927. It was kind of forgotten to history for a while, at least for all people except for a small subgroup. And then it was reinvented in some other communities twice in 1970. And so there was two groups that invented it, Carroll and Chang at Bell Labs, and then they called it canonical decomposition. And so that was CanDecomp, this awesome name. And then Richard Harshman at the same time invented it as well, and he called it parallel factor analysis, or ParaFac. For many years, people would write papers where they call it one or the other. When I first started in this field, I did not realize that these were the same thing right away. And so it was quite the revelation. In 2000, a guy named Hank Kears suggested that we compromise and just call this thing CP to acknowledge both of these early papers, again, not knowing about Hitchcock, so that was the idea. In 2010, folks started calling it canonical polyadic decomposition. I don't know who was the first, but it was in several papers starting in 2010 by Pierre Camon, Levin de Lathauer, and others. They sort of cleverly reverse engineered CP to mean canonical polyadic. Polyadic goes back to this sort of nice paper by Hitchcock. It talks about the polyadics. And so I thought this is sort of a nice reinvention of this term. I was sort of interested, especially in preparing for this talk, to figure out who Zhizhi Chang was. So if you look up Hitchcock, he has a Wikipedia page. Both Carroll and Harshman have very nice articles about them after they died. But Zhizhi Chang was a bit of a mystery. So Zhizhi was a female member of the technical staff at Bell Labs. At that time, women were not hired into the same technical roles as men, although they were quite welcome to be the programmers. And her role as a programmer is widely acknowledged because in 1970, this was not unusual that this was considered the work of women. Funny today, I still love programming, but it's not, now maybe it's less considered that way. So I was able to sort of reach out to some people at Bell Labs, including Fan Chung Graham, and actually get in touch with people that she worked with her former husband, with her niece, and even with her daughter. And so I was able to find out a little bit more about Zhizhi, and people have only wonderful things to say about her. I'll just give you the facts for now, but perhaps we'll be able to get some more information in the future. She was born in 1927 and died in 2007, emigrated to the US from China, was a really prolific researcher. She actually has quite a few papers to her name, including several single-author papers about her software. And then I was able to get from her daughter this really nice picture of her working with Doug Carroll back when they were working together in the 70s. So this is sort of a nice story of a bit of a hidden figure, at least to me, in the tensor world. So now I'm going to motivate some of this idea of CP as a tool for data analysis. So Alex Williams is a graduate student at Stanford in the neuroscience group that came to work with me. His group, a group of Mark Schnitzer at Stanford, is collecting some really novel data based on a device that they invented that can measure the activity of multiple neurons at once in the mouse, the brain of a mouse as it's moving around in a maze. And so at each moment in time, they get an image, something like what you see here. Through no small amount of work, they get to this vector. And so I actually asked them, well, how hard was it to pre-process the data? And they said about 2 years. So 2 years of graduate student postdoc work, they make this lovely set of numbers out of this measured image. And that's what we start with. So for 300 neurons, they have sort of an activation level for every neuron. And they do this over time as the mouse is moving throughout the maze. And so we have a neuron by time matrix where we have the activation level of each neuron at each time. That is one trial of the mouse going through the maze. Then they do that over and over and over again, 600 times, because they want to understand learning. And so then there becomes this question of how do you analyze this type of data? So let me tell you a little bit more about the experiments that they did here. So we have this mouse will start in either the west or the east of this maze. There's a wall in the middle, so that when it gets to the middle, it has to make a turn. And if it makes the correct turn, it gets a treat. And so at first, it should always turn south, whether or not it starts in the east or the west. Otherwise, so he goes along and he does that for a bunch of trials. Then they change the rules. And isn't that just how life goes? The rules are just changing in the middle of your life, and then you have to switch your behavior. And so then the mouse should turn right. So nothing changes if the mouse starts in the west, but if it starts in the east, it needs to turn north to get its treat. Then they change the rules again, and the mouse should figure out the new set of rules to get its treat. And so that's the setup. So we get something out of tensor decomposition that looks like this chart. So now you're thinking, I should have sat closer to the front. and you can feel free to move. So what is this thing? So we're making this tensor decomposition, which looks like this. And so let's just look at the second component. This first plot over on the left is the activation of each neuron, in a sense, that corresponds to the vector in mode 1. Then we see a profile in time, which corresponds to the sort of activity in time. And notice that this curve is smooth. We did nothing to make this smooth. This is just inherent in the data. And then last is this funny business with the different trials, which are coded with different markers to say what's going on. And so it's orange if the mouse started in the east, green if the mouse started in the west. Those are sort of equally spread out. Then it's a circle if it ended in the south, which is where it ended most of the time. And then it's a square if it ended in the north. And then it's filled in if it got its treat, and it's empty if it didn't get its treat. So, do we see anything here? Well, let's zoom in on this third factor here. And you can see in time, it's happening sort of towards the end. And then there's a very clear separation. I can draw a line between the filled-in markers and the not filled-in markers. So my guess is that these are the neurons that have to do with whether or not that mouse got its treat. So I call those the happy neurons. If we look down here at this second to last one, this is sort of towards the beginning of time, and in fact, we see a very clear separation between the green and the red, and the orange and the green, and that corresponds to the starting position. So these are the neurons that somehow understand where the mouse has started. If we look at the last one, this is towards the end, and it's a little bit hard to see the shapes, but the tops are the squares, and the bottoms are the circles. And whether or not they're filled in, they're still sort of separated here. Squares are always on top. That's where the mouse actually ended. Circles are on the bottom. And so this is the sort of set of neurons that understands where the mouse ended. So this is very interesting. The tensor decomposition knew nothing of the conditions of the trials at all, and yet somehow it saw this underlying behavior in this low-rank structure. So this is sort of the utility of these methods, and the neuron people are extremely excited. There's a paper about it on bioRxiv, and the references in the slides. So how do we actually compute this thing? Let me say a few words about that. So we want to fit this CP model. We are given our data X. We want to build a model M. It has the matrices A, B, and C that we want to find. So if we write it directly out, we get this equation at the bottom that we want to minimize. We want to find A, B, and C to minimize this equation. That's kind of ugly looking, but we can do some tricks. So first let me tell you a little bit about this. If we want to determine how many of these components we have, the R, if you want to do that exactly for some given tensor, even a very small tensor, this is NP hard. And in many cases, it seems to be impossible, even for really small tensors, the infamous 9 by 9 by 9 tensor that we don't know the rank of. And in fact, you might say, well, I don't care, and I often say this, I just need an approximation to this thing. But even that can be ill-posed unless you put some conditions on it, so we make sure to add those. The approximations you get are not nested. So the best rank 1 may have nothing to do with the best rank 2, which may have nothing to do with the best rank 3. This just means more computation. So you have to do it for every single rank that you're interested in. And especially when you don't know the rank, you usually want to try a few. One key thing, especially for linear algebra folks who are used to the singular value decomposition or principal component analysis, the A, B, and C that you get are not orthogonal. And so this is a bit unusual. There are a lot of papers that make orthogonality assumptions, and there are some applications where that holds true. But most of the time in real-world data, we cannot make any assumption about these vectors that comprise these factor matrices being orthogonal. And I just think that makes it a more interesting problem. One benefit you get that you don't have with matrices, where you sort of impose an orthogonality constraint, is that these matrices you get are unique up to certain conditions, which is you can always swap 2 of the components. That's just an ordering. And you can also sort of scale an A by 2 and a B by a half, and it's the same thing. But up to these trivial ambiguities of scaling and permutation, the factor matrices are often unique, especially in the case where the number of vectors is small compared to the size of the matrix. And so that means it makes it much more interpretable when you're trying to analyze data. And principal component analysis, for those who have used it in data analysis, can be very hard because you can rotate the factors and still get equivalent solutions. Now you cannot. So how do we actually fit this model? We use a method called alternating least squares, and that's because if we stare at this equation and just think of what's going on with respect to A, if we fix B and C, we can stare at this and convince ourselves it's just a linear least squares problem. And so that makes it nice and easy to solve. We can do the same for B, fixing A and C, do the same for C, fixing A and B, and then we just keep doing that until we get to convergence. And so that's an alternating least squares algorithm. And the function value is monotonically decreasing throughout, and so you just sort of continue until you cease to see any improvement in your fit function. This is a non-convex problem, so those are always a little bit scary, but every subproblem is convex, and moreover, it's actually exactly solvable because it's this least squares problem. So let's look a little bit more in detail at the least squares problem here. So we want to solve this least squares problem. I'm going to write it in sort of ugly notation, and I don't require you to know this notation. I'll also show it in pictures. So we have this matrix over on the left. So we took that three-way array, and we rearranged it as a two-way array. So we can rearrange it however we want. So we're going to rearrange it as a two-way array that's called the tensor unfolding to a matrix, or the matrix unfolding of the tensor. And we're going to put the first mode that will correspond to the rows, and everything else will correspond to the columns. We want to solve for the set of vectors in the matrix A. And then we have this sort of combination of the B and the C, this funny thing. We combine that into something called a matrix Cauchy-Rao product. It doesn't matter what that is. Except for sort of Kronecker products along the rows. But these are just details. Just think of everything else as shoved into that matrix. This is a least squares problem, but it's sort of backwards and sideways to what we normally think of. So we have the matrix of the least squares problem on the right, and the right-hand side is on the left, just in case it doesn't look familiar to you. The big thing is it's a short and very wide matrix, or if we flip it, it's a tall and skinny matrix. And how bad is it? So if we have an n by n by n problem, then our matrix is r by n squares, where r is the number of components. Well, that's not so bad, just n squared. But if it was a d-way tensor, it's r times n to the d minus 1. So this gets very wide very fast. And it's actually a very overdetermined problem. So maybe there's something we can do about that. So one thing we can do is do randomization. And this is a very powerful tool that's getting a lot of steam. So the idea that we can do in this case is just pick a subset of the columns of the matrix and then the corresponding entries in the right-hand side, which is on the left, and solve this smaller problem. And so we can do that with a sampling operator. Now, if you just do this naively, it doesn't look so good. So as always in algorithms, the devil is in the details of how you actually implement things. But I want to stress that one of the neat things about this is we have very strong mathematics that tell us how good the solution is. This is not just a heuristic idea. We can actually bound the quality of the solution based on properties of the original matrix and how many of these samples we take. So this makes it very powerful. There are a few details. We don't actually create the unfolded matrix in computer memory. We actually just keep it in its tensor form and pull out just a few elements we need. Similarly, on the matrix side, we don't actually ever form this funny matrix, this funny Cauchy-Rao matrix, because there's actually some computation to forming it and some memory movement, so we avoid that and just pull out the pieces we need. In sort of computation these days, the thing you actually worry about almost more than how many operations you do is how much memory you move around. And so we are avoiding that as much as possible. There's also a huge detail, which I am not going to go into today, but your matrix has to have certain properties for this to work. It has to be suitably incoherent. The thing to know is that you can always fix that up by applying a Johnson-Linienstrass transform. Just doing that would be slow, but then they have these magical things called fast Johnson-Linienstrass transforms, which involve, say, FFTs or some fast transform, and then a random diagonal sign matrix, and you are in business. And so we can add on what we call mixing everything up so it's incoherent, and then this theory about how accurate the solutions are is guaranteed to hold. So it turned out that this worked great. And then the sticking point, in fact, it was so great, we're like, wow, everything's so fast. And then we realized that we had a sticking point, which was checking convergence. So whoops, didn't think about that one. And so what could we do for that? So we'll take another idea of randomization, but a different approach, and figure out how we want to check if this function value has stopped improving. So it's a very simple idea, a very old-fashioned idea. Just take a poll. So this is like polling voters on election day. We're just going to look at a few of the entries randomly sampled, and then we can sort of bound how accurate our estimate is using Chernoff-Hufting theory. So we actually know how many samples to take. We have some idea of how accurate our answer is. And we can sort of do an f-hat, an estimate of the original. That is, and then we just use this omega to scale things up so it's sort of the same size since we've only looked at a few entries. And we can make a great estimate. And so how good is it in practice? We use just, say, 16,000 samples on a 5-way tensor that has size ranging from 5 to the 5th up to 60th to the 5th. So even in the smallest case, the 5 to the 5th, we're only using less than 1% of that data with 16,000 samples. We're always accurate, a relative accuracy of at least 10 to the minus 3 with only these 16,000 samples. And we can get speedups on this relatively small tensor of up to 300x. And so this is sort of a nice idea, maybe even independent of all the other stuff that we've talked about. You can sort of check values of functions, but just sampling a few entries. So let me show you another example of this applied to real data. So we were motivated to this because sometimes our data sets are somewhat large. So there's this hazardous gas data set where they are looking at gases released in a room. And so they want to know if there's a hazardous gas. If there was a hazardous gas in this room right now, you would want to know. So they want to release the gas and then measure sort of the gas flowing over these sensors in time and being able to tell if they can detect what's going on. So we have 71 sensors. It's actually 72 arranged in a 9 by 4 by 2 grid, but one of the sensors was bad, so we didn't use it. There's 5,000 points in time. This is sort of downsampled from the original data. They run the experiment at 5 different temperatures to make sure it works in all cases. And we did 140, well, the folks who did this did 140 experiments. All this data, which is just this big pile of numbers, is 2 gigabytes of data. And we want to see if we can make sense of that, but that's rather big. So if we use our regular method, it takes over a minute. And this is sort of at getting close to the limits of what we can do. If we use the randomized method, we get at least a factor of 2x speed up. And as the data set gets bigger, the factor is much higher. And that just takes less than half a minute. And what do we get? So in fact, the answers that we get from these are indistinguishable. So I'll just show you the ones from the randomized method. So we get this sort of sensors. And you can see there's some patterning here, which sort of reflects this 9 by 4 by 2 pattern, even though we didn't tell the tensor analysis. You get these profiles in time. And you notice several of them don't pick up until partway through. And that's because they don't actually release the gas at the beginning of the run. They wait a little bit, and then they release the gas. So we can see that behavior there. There's different things going on with the heat. And then we have a bunch of different experiments. The top one is just sort of a background condition to me because it's constant. It doesn't matter when you release the gas, but then other things start happening. So this is really a matrix of size 140 by 7, so 140 experiments, 7 factors. So we can throw that into a PCA projection. So we project this down to 2D and see if that helps us make sense of what we're seeing, because there's a lot going on. And so we get these blobs. So we could be a psychologist. What do you see in these blobs? But let's just see if it means anything. And in fact, when we labeled what gases were released, there's a very clear sort of separation of the different gases into these appropriate blobs. And in fact, if you didn't know what your data was, which happens more than you might think in your experiment, you would see that there is this underlying structure. Okay, so we've talked a little bit about neurons and gases and fitting and using randomized methods. One thing that had bothered me for many years was this idea of why use squared error. It seemed like there are other metrics to use. And in fact, in many of our applications, we had people coming to us with data that did not look like continuous Gaussian data at all. So we had to start asking, what else can we do? So we looked at the goodness of fit criteria. So we have this squared error. Maybe we could replace that with just sort of an arbitrary function at every element, look at a little function of the data and the model estimate at that point. Maybe we could swap out that function. Instead of doing x minus m squared, we could use something else. So where does x minus m squared even come from? So what you often hear if you talk to people who do this is I have data that has low rank structure plus Gaussian noise. And so what they really mean there is they have data that's normal distributed with mean 0 and standard deviation sigma. That's their model of their noise, their epsilon. You could write this a different way where for every point, the model that we're building is an estimate of the mean value of that point, and we know there's some standard deviation sigma. And sigma is assumed to be constant throughout. So what this is saying is we have these little curves. That's our estimate of the mean. And we think that our data is somewhere in that narrow region defined by the sigma. And so we can sort of describe the likelihood of observing an x given a mean mu using the probability distribution function that's in terms of mu and sigma. So let's suppose that we take our model to estimate that mean. So at every ijk, our model estimates the mean. The model is required to have low rank structure. So it has this structure, and then we plug this into this probability distribution function at every single point, and we multiply all these likelihoods together, and then we get this likelihood. But you don't work directly with that. It's the product of a lot of annoying things that are small. Those do not compute. Instead, you take the log of that, which is a monotonic function. It swaps your product for a sum. And then just for convention, you take the negative. So instead of maximizing the likelihood, we're minimizing the negative log likelihood, which is this formula here. So if we stare at that a while, and we say, oh yeah, sigma is constant, throw that out, then we're back to our sum of squared errors that we know and love, and there's good reasons to love it. But sometimes it's not appropriate. So for example, what if your data is non-negative? So you have your xi, j, k's are all positive, all greater than or equal to 0. What can you do? So Gaussian feels a bit wrong because you could have a mean that's like 0.1, and then it's very easy to see negative entries. So there's another distribution, well, there's many distributions, but I just like, for these days, the Rayleigh distribution. And so it looks like what you see over on the right, that you sort of have all your data distributed in this sort of hump that can't go to the left past 0. And so the probability distribution function for that is in terms of a sigma. It's a sort of a different but related sigma to the normal distribution, but that's just how the statisticians write it. And so we can estimate our data ijk is Rayleigh distributed with this parameter defined by mij, which is the sigma here. So we can minimize this negative log likelihood. If we remember that the x is constant, so it doesn't affect our optimization in terms of m, then we get this funny-looking goodness of fit function here that we want to minimize. This requires that the model is positive, but this is easy to enforce if we just choose the a, b, and c to be positive, because we're just multiplying them together. So we can enforce non-negativity easily. The expected value of your x is not exactly the m. It's this funny scaling of it. Of course, we could fold that scaling into the probability distribution function, but it doesn't make any difference. So it's just something to know. What if your data is even more interesting? What if it's not even continuous, it's discrete? What if you have binary data, just zeros and ones? This happens a lot. We'll give an example with the graph. What do you do in that case? So let's talk about probabilities for a minute. Those of you who have gone to Vegas may go to sleep now. Most of us don't spend a lot of time in Vegas, so let me tell you. So you have your probability between 0 and 1 of something happening. You can equivalently talk about the odds of it happening. So if you know the probability, the odds are the probability divided by 1 minus the probability. If you have the odds, you can figure out the probability as just the odds over 1 plus the odds. Okay, so you can easily go back and forth between the two. When you think of the likelihood of seeing a 0 or 1, it's just the probability to the power 1. And the probability of seeing a 0 is just 1 minus the probability to the power 1 minus x. That's the easy way to write it, but I'm going to write it in terms of the odds. And so that's this funny-looking expression on the left in terms of r over 1 plus r to the x, and 1 over 1 plus r to the 1 minus x. So it looks a little uglier, but trust me, I think it's, well, it's an opinion. I think it's better. You may not. So mij is the odds ratio of observing x equals 1, xijk equals 1. And so xijk, we're saying it's Bernoulli distributed with the probability given as the function of this odds. And so the expected value of x at the end is the value of the model over 1 plus the model. And so we can plug everything in to this probability mass function. Because it's discrete, we call it a PMF. And we get the objective function here. And then we require that the model be non-negative, which I said before is easy. So why is this easier than working directly with these probabilities that are between 0 and 1? That introduces a very ugly linear constraint, and that we don't want to have to worry about. So this makes our lives much easier to work with the odds, and it seems a little bit more interpretable to me as well. So we have this idea of a generalized CP model that we can switch out different objective functions. And I sort of say, I don't want to judge your objective function. Use the one you like. I work with a lot of analysts. They have favorite objective functions. We wanted to give them a flexible framework so they could use any objective function they want. We have the 3 we just discussed here. There's others there's one that's based on for count data, Poisson likelihoods. Similar ideas have been introduced in the matrix world. I won't go into the details of the algorithms. I'll just mention a few notes. This method can be solved as before in an alternating least squares problem, but because these subproblems are not closed form, there's less benefit in doing it, so you can also do what we call all-at-once optimization. And especially when you have missing data, which we often have, that is something you generally want to consider. In that case, instead of summing over every element, you just sum over every element you know. So we denote that set as an omega here. The gradient has a very elegant form. In tensor language, we say it has an MTTKRP. You don't even want to know what that is, but if you do, come talk to me afterwards. But it's an important key kernel in tensor computations. And it's neat that it shows up again in these generalized forms. Missing data turns out to be very easy to handle in the sum form I mentioned. The interesting piece is it also introduces zeros into part of the gradient computation wherever there's missing data, which means we sort of get this sparsity in the gradient computation. This turns out to be something we can exploit if we have very large-scale data and we want to use, say, a stochastic optimization method to solve. We can actually get a sparsity in the gradient computation, which makes it much faster to compute. And so then we can exploit that and get very nice computations. And so this is all very elegant, but I won't go into these details here. I'll just give you a few examples. So let's go back to that mouse data. That was actually non-negative data. And so we put this through the non-negative thing, and we got something different. Which is better? It's really a matter of opinion. So the folks that we were working with, the neuroscientists, they did not like negative values. And I have to tell you, I sympathize with them. I don't really like interpreting negative values either. But in some ways, it's easier. Here, we get a different set of nodes. Let's see. So if we look at the 3rd, that's starting east. And we look at the 5th, that's starting west. Before, that was all in one piece, but now it's in 2. So that's good or bad, depending on your point of view. But we don't judge the choice of fitting function. You can see that south and north became the first and the last. North didn't happen very often, so that's why it's sort of a lower power. And the incorrectness was second and split there. So it's just a different way of looking at your data, but it pulls out most of the same features. The gas data, one thing I didn't tell you about that gas data is there's actually a lot of missing entries. These sensors are flaky beasts. And so we actually did some tricky stuff to fill in those missing entries, which you don't normally want to do. We could handle it directly using this method, and it actually also happened to be non-negative, so we also use this Rayleigh distribution again. And so we get sort of similar results to before, but it's all non-negative. So it makes it a little bit easier to interpret for an analyst. What about graph data? So what if we had this data set that comes from a chat network of students at UC Irvine. We arranged it as a 4-way tensor. So there was senders and receivers in this chat. Then there was messages collected every hour of the day over a series of about 200 days. And so we got this very sparse tensor. It had about 15,000 non-zeros, and we wanted to analyze what is happening there. And so there was a 1 if student A and B chatted during hour Y of day Z. So we used this Boolean odds function that I talked about before, so Boolean data. We're going to estimate the odds that we see a 1, and then we do a rank 12 decomposition. And we see some structure here, which sort of seems reasonable. So we've ordered the senders according to which component they are the largest magnitude in. The receivers are just ordered the same way, so you can see there's some symmetry in the components, groups talking amongst themselves. You can see things happening in time. So some of these were clearly about limited term projects, which happened in maybe a few days or a couple weeks. Some things lasted for longer. There is a break in the time, so around 75 to to 90. There's a break in the days, and actually we went back and looked, and that was some sort of semester break at the university. So you can sort of see what's happening in your data. So I think this is all for the examples. Before I get to my conclusions, I'm going to give one sort of ad from our sponsor and also an ad from me. SIAM is going to be starting a new journal. This was just approved last month, so in fact, we're in the process of putting together advertisement material that will go online and so forth, but you get to hear about it here first. So it'll be a SIAM journal on the mathematics of data science. It will launch sometime in spring 2018. The focus will be on the role of mathematics in data science, is complemented by all the fields you know are very important: computer science, statistics, signal processing, and network science. So I will be the editor-in-chief. We've lined up a set of great section editors. We're in the process of putting together an editorial board, and I hope you will keep your eye out for that and think about submitting papers and encouraging your colleagues to do likewise. So I'll close and just acknowledging my collaborators again and talking a little about the benefits of CP, tensor decomposition, and data analysis. It's a very useful tool for real-world data analysis. It gives sort of an idea of latent sort of factors in your data, things that can explain your data. And it can be used also for dimensionality reduction and putting it into subsequent analysis like the PCA visualization we showed. Randomized methods are becoming a big, important tool for us because of the size of the data sets that need to be analyzed. And there's a lot of interesting mathematics and statistics and applied math and computational issues there. We talked a little bit about flexing the way that you measure the fit to handle different data types. And I'll say if you get the opportunity to work with real data, it can be ugly in so many ways, but you need to understand how it's distributed and how your model fits to that data. Measuring that is an important part of data analysis. There's many, 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 many open math problems of all shapes and sizes. We use sort of pure theory a lot. We use algorithm and computation a lot. It's all useful in the world of data science. I'll give you a few links. There's a thing called Tensor Toolbox for MATLAB where you can play around with tensors on your own data. We even have parallel implementations in progress, and you can always contact me by going to my webpage and get my email. Thanks again to SIAM for inviting me, and to all of you for coming today. Thanks.
We have a few minutes for questions. If someone wants to ask a question, we ask that you come forward to one of the microphones in the aisles towards the front.
So back to that slide with convergence check. You were talking about a bottleneck there, and you said that you have decided to stick with just some random subsets of elements in function evaluation. So my question was, on each iteration, was it the same subsets, or you have?
Yes. Okay. Yeah. So the question is that when we're doing the subsample of elements to estimate our convergence, or if we had gotten to convergence, what's the same subsample? And I did not say that, but actually, yes. On that, we use the same subsample every time. For the least squares problems, we use a different set of random columns every time. But we kept that one fixed because it was just much easier to do.
So you have mentioned that then you could evaluate the probability of your convergence by using Chernoff bounds. Mm-hmm. If you're using different subset every time, it's still applicable?
It's applicable, but there's enough variance that it becomes difficult to really be confident about convergence. So in these randomized method, whether it's matrix sketching, using this iterative context, or the stochastic optimization methods, checking when you're converged is probably the most difficult part.
Thank you.
Mm-hmm.
Any other questions?
You know that we can get a lot of weights from training neural networks in deep learning. Do you think your method would be able to apply to understand the structure of the weights you obtain from deep learning? Are you aware of any work done in that direction?
So you're asking if we can use the tensor analysis to understand the networks that come out of?
The weights of a neural network, they
right.
form matrix as well.
So I'm not aware off the top of my head. It's kind of on my reading list to look at that. But there are a lot of connections between tensor analysis and deep neural networks, and folks are looking into that, but I'm not fully up to date on everything that's happening right now.
Okay, so I also have a question. When you try to solve the generalized CP problem, do you think if there's any opportunities for the Bayesian analysis?
Oh, for generalized CP, is there opportunity for Bayesian analysis? Absolutely. Yeah, that would be great. But Bayesian analysis tends to get a bit more expensive. So, but I think there's definitely opportunities there.
Okay, thank you.
Oh, hi, great talk.
Where are you?
Hi, I'm here. So I'm working on networks and hypergraphs, which can be represented as tensors. And I'm mainly using Tensor decomposition. So I'm thinking, why you choose CP instead of Tensor decomposition, and can you just generalize or just apply everything here to the Tensor decomposition? Thank you.
Yep, so I really like Tensor decomposition. I didn't talk about it today, but I often use it for compression of data. I find that it's harder to use when you're trying to look at the components because it's not unique anymore. So Tensor decomposition, there's a rotational ambiguity which you don't have in CP. And so CP is a bit harder to compute, and there's various theoretical problems that I mentioned, but those don't exist for Tensor. So people do either one, but they're not interchangeable. And so I would encourage you maybe to try the other just for fun.
Thank you.
One last question.
Yeah, for the matrix, we have a sparse matrix, so you take a sparsity of the data. So for the tensor, do you have this sparse tensor?
Yeah, so there are sparse tensors. That was actually one of the first things I worked on because I was surprised there was no sparse data formats for tensors, and it made working with large-scale sparse tensors impossible. And there's become now a big interest in what are the right data structures to do for sparse tensors. And so when I mentioned that key kernel MTT-KRP, there's a few key kernels that have been identified now, and people are researching what are the best data structures in these cases, including our group. But it's an open problem.
So if anyone has any further questions, I encourage you to talk to Tammy after the lecture, and let's thank her once again for an informative and interesting lecture.